learning experience for me. This is my first ESIP meeting, and I want to especially thank Thomas for inviting me and our group to come and present here. So I'm going to talk about our own homegrown solutions to big data. So what are we looking at here? This swirly red and blue stuff is the ocean. It's a simulation of the ocean. It's the vorticity field, and it is up there to show something about the complexity of the type of data sets that we deal with. Now, this morning we heard a lot about stakeholders, people, like the people in Africa who need their rainfall information, droughts. I represent a very kind of other endpoint of the users of science data. So we are trying to use earth science data to make discoveries about nature. We are doing basic fundamental science, and we're also choking on big data. So let's look at more in detail at this sort of model. So this is the model simulation that generated that that image that I showed you before. So this is a simulation of the ocean that was run by colleagues at NASA JPL for the SWAT mission. And what we're looking at is the speed of ocean currents. And this is a global 2-kilometer mesh simulation that includes a full suite of tides. And it is a really groundbreaking opportunity for science. This is a virtual laboratory that allows us to explore scientific questions in a way that has never been possible before. This simulation was 1 year, and they generated 2 petabytes of data. This is just one hypothetical, science-driven simulation that was done. The things we can potentially do with this are answer really important questions like what are the sources of energy and sinks of energy for ocean currents? What are the interactions between processes at different scales like tides and eddies with the global overturning circulation? And those ultimately feed back on questions like how much heat will the ocean absorb in the coming decades? How much carbon dioxide? So they connect to the really big picture questions about climate change. But our ability to work with these data sets is severely limited by the size of those data sets. So that problem is why I, as a physical oceanographer, had to become a big data person. So what I'm going to do in my talk is tell you about that journey and some of the tools that we've been working with. So I discovered this big data problem in 2013. When that simulation was run. And I said, oh my God, this is amazing. I want to ask all these science questions from this simulation. And I couldn't do anything with it. I didn't have spare 2 petabytes of hard drives to download the model onto. I didn't really have a set of algorithms or tools I could use to analyze the data in place. And so I kind of wandered around. I experimented with my own kind of roll my own big data solutions, parallel processing. I'm a scrappy guy. I coded up some stuff and I tried to get it to work. And this is what practicing scientists do. We're used to just doing things on our own and not necessarily using all the frameworks and tools that may be out there. That's the culture that I come from. I had a hallelujah moment in early 2015 when I discovered a Python package called Xarray. And I'm going to spend most of my talk talking about what Xarray is. Just to give some context to this, so Xarray is part of the open source scientific Python ecosystem. Now I have a few graphs on the screen from analysis on Stack Overflow. The one on the left shows that Python is the fastest growing programming language at use today, at least measured by questions asked on Stack Overflow. Another interpretation is maybe it just has the worst documentation. But it's pretty clear Python is growing very rapidly. And then within Python, what part of Python is growing? Well, it's really the data science part. So those curves on the right, the exponentially growing one is pandas, We've also got NumPy, Matplotlib. So if scientists in my field are not using MATLAB, they are using these tools, scientific Python. And not just in my field, astronomy, bioinformatics, and of course industry, the exploding world of data science. And that's what's driving a lot of this development and growth. So scientific Python is organized as a series of layers. This is a slide I stole from Jake Vanderplas. And at the core there's Python, but then there are many other packages that sit on top of that Python, providing different things like numerical arrays, visualization, data frames, etc. And Xarray is one of these layers. And on the top of this, of course, we have a growing range of Python geoscientific software. And I put this up here just to highlight the fact that, cultivating this ecosystem, in my view, is very important for, the success of my science. Okay, so what does Xarray do? Xarray really combines these three technologies. And Xarray represents the data model of netCDF and CF conventions within Python. So an Xarray data set consists of data variables, coordinates which describe those variables, and other attributes. So it's been described sort of like a netCDF file meets a pandas data frame. And Xarray was created by Stefan Hoyer of Google. And what can we do with this? Well, Xarray makes doing science with this type of data really easy. So I can load a data set like this, and I see a representation of what the coordinates and variables are inside that data set. And then I can do really simple selection. So if I want to know what the sea surface temperature field was on my birthday, I can just ask it and plot it immediately in one line of code. I say this because a lot of the times when we think we need a GUI interface or a fancy way to let users interact with data, in fact, Xarray is often so simple enough that the users are happy to just write code. And I think we're all better off in that scenario than trying to build a bunch of viewers for our data. So we can do more label-based stuff, like easily take a mean over this data in time and longitude and plot it, one-liner. And then in 4 lines, I can compute the Nino 3.4 index. So here I do some grouping by month to define a climatology. I then define an anomaly as the difference by that. Select the Nino 3.4 region. This is a region in the middle of the tropical Pacific that's used to measure the intensity of El Nino. So I average over this little piece of the globe, apply a rolling mean, and plot it. And I get the exact same thing as what's on the NOAA website. So these are just some examples of how this makes it really easy and efficient for scientists to work with data. That's why we like it, and that's why it's growing very quickly in my field. At the same time, it doesn't limit us. We can apply any arbitrary functions to this data. Okay, and just for this community, it's worth mentioning, Xarray can also read geotiffs. Okay, so there's a wide range of input and output formats. So to summarize Xarray, we have label-based indexing and arithmetic, good interoperability with the sort of core scientific Python packages. Xarray has this great out-of-core parallel computation ability, and that's where the big data part comes in. And the subsequent talk by Matt Rocklin is going to talk a lot more about this. A wide range of input-output options, netCDF being the sort of gold standard, and a lot of sampling aggregation tools that are really useful that are borrowed mostly from pandas. So after discovering Xarray, I had this incredibly productive year where I was able to use it for all my science and get a lot more done more quickly, and also connect with the great development community around this tool. And we held a workshop because a lot of us realized we were working on similar things and needed similar tools. So we held a workshop at Columbia in late 2016. And at that workshop, we came up with some goals for what we now call the Pangeo project, which is just an effort to coordinate a bunch of efforts and prevent us from duplicating each other's efforts. So the first one is just to foster collaboration around open source scientific Python for ocean, atmosphere, and climate science. Encourage this ecosystem to develop more. We need to build out the stack of domain-specific packages, so things like thermodynamics, regridding, all the things we need to do in geoscience that they don't need to do in finance, so no one has built a tool for that yet. And what I'm really going to focus on here today, and Matt's talk will talk a lot more about, is we wanted to scale Xarray and Dask from the medium data they were already good at, hundreds of gigabytes perhaps, to big data. We have petabytes of data, and we want to use the same tool to look at it and analyze it. So in order to support that, we wrote a proposal to NSF, to EarthCube, in the beginning of 2017, and that was funded, and it's been going on for about 6 months. And this team is a subset of the full community. It involves collaborators from my institution, Columbia, Lamont Doherty Earth Observatory, NCAR, and Anaconda, formerly Continuum, which is a leading developer of scientific Python open source tools. So we're working on this scaling thing, and there's also many collaborators outside of this team. So this is a community effort. Okay, so what are we doing in this EarthCube sponsored work? Well, there's a lot of architecture diagrams. This is our architecture diagram. It's pretty simple. We don't think it needs to be too complicated. So in order to do big data science in the cloud, what we need is a way to execute code remotely. That's our Jupyter notebook. We need a data model that represents the data structures that we need in earth science and provides computational operations that are relevant to those. That's Xarray. And then we need some parallel scheduling that allows us to scale out those things. And that's what Dask does. And then behind this all, we need to store the data in a distributed file system that will not, as Thomas nicely pointed out, provide an I/O bottleneck on whatever analysis we want to do. So this basically already works. It already worked before we even wrote the proposal. What we're just doing is trying to make it work a little better and support the community around it. We have been deploying this on traditional supercomputers, HPC systems like NCAR, Cheyenne, which is where a lot of big Earth science data already lives, especially if it's coming from simulations. And we also have credits from Google via NSF's Big Data program to deploy this in Google Cloud Platform. And Matt's going to give you a demo of that in his talk. So I'll just wrap up here. Here's the messages from our community to the ESIP community. The scientific Python ecosystem is what science users want to use to analyze data. This is the tool we want. It's that or MATLAB, and MATLAB, is declining, and this is ascending. Scientists like to do their own stuff. They don't like a lot of pre-canned, predefined routines or new scripting languages. It's hard enough to leave MATLAB and come to Python. So we want to write our analysis code in scientific Python. So Xarray takes a long-standing data model, NetCDF and CF conventions, which is very successful in our field, and turns it into a flexible computational tool for doing big data analytics. There's a lot of data providers out there. We need to be able to read your data with Xarray. Okay, this is very important. If you're using standard formats like NetCDF, HDF, or providing data through OpenDAP, we can do that. If you're coming up with a new API for data access, we can't. So that's a clear opportunity for collaboration and dialogue to make sure Xarray can read that data. And it's easy to write a new backend for Xarray if your data fits this data model. So please collaborate with us and engage with us on our GitHub site, where we have a lot of mostly discussion, not much code. That's in all the other repositories. Thank you. Oh, yeah.
Do you have any questions?
Yeah, sure.
Okay, I'm just sending me the questions.
Yeah, hi. You mentioned Google Cloud and Cheyenne. If I put a bunch of data on Amazon, can I also use your stuff?
Yeah, if you can pay for the compute. So we believe very strongly that the requester pays model is a great way forward. So if the data is stored on the cloud in an open format and it's requester pays, you can spin up this cluster yourself very easily and compute on it. if someone has Amazon credits that they want to use to deploy this, and we can put this on your Amazon project, it's all runs on Kubernetes. Matt will talk about it a lot more, so it should be pretty trivial to deploy. Okay, yeah, sorry.
All right.
Is Xarray compatible with Parquet?
You should ask me that question.
Yeah, I don't think so yet.
I mean, we'll talk about that in a second. Dask is the that's the thing you want to do.
Have you had any experience trying to put multi-resolution data into Xarray where it's not nicely gridded?
No, you can put anything that's the CF conventions support. I don't believe that they support multi-resolution data, and so you would need a different type of data structure than a regular multi-dimensional array. It's a big problem for unstructured grids and stuff.
It is not. But maybe that matters.
You're good. You're good.
You want me off by 12:25?
Yeah, day one, you're off by 12:30.
Okay. Well, I'll shoot for 12:30.
All right, so we got Matthew to more discussion about Dask. One thing, since I'm new on Dask and Xarray, my first question to his team is looking at, well, how do you manage this stuff when you deploy into cloud, right? And I think hopefully you can shed some light to this.
Yeah, sure. I'm going to try to move this, maybe. Is that? Okay. Let's see. Is this audible from the web audio? I'm just going to stand here for a moment. I'm going to give a general, hi everyone, I'm Matthew Rocklin. Thank you so much for having me. You cannot hear me?
No, I can.
You can, okay, great, thank you.
Sorry.
Yeah. Hi everyone, and it's Matthew Rocklin. I'm an open source software developer in the Python ecosystem. So I work with libraries like NumPy and Pandas and scikit-learn and Jupyter. And my role is more or less to try to parallelize and scale them. I work for Anaconda, which is a for-profit company, so don't trust anything I say. But I'm much more on the open source side of that company, not on the profit side. So I maintain development of Dask along with many other people. So I was also going to talk about Xarray and JupyterHub. And my job is more or less to make Ryan's life easier and other people. So usually when I talk about Dask, I'm talking to banks or finance companies or someone who cares about tabular data. So I usually start with trying to scale pandas. So very briefly, Dask data frame is library for parallel computing. We're talking about it for a little bit. We're going to talk about cloud stuff afterwards. So if you want to scale pandas, one way to do it is put many pandas data frames on many different computers and manage them very effectively. And Dask allows you to do that. Dask also allows you to manage many different NumPy arrays, many different multidimensional arrays, the same you'd find in MATLAB or R, on many different computers in a cluster or on your hard drive. So Ryan has been using Xarray for years without a cluster to analyze 10 to 100 gigabyte data sets on his laptop. So Dask Array provides a NumPy abstraction. It looks and feels just like NumPy. It uses NumPy under the hood, but it is composed of many different NumPy arrays spread around a cluster. Okay, so I'm not hearing. So I should try. Thank you so much for saying that, by the way. I'm going to try, actually, just to move this over here. All the wires are still the same. Is that okay?
Or do you want to, can you?
I'm going to be typing, so handheld is going to be difficult.
Oh, you do. Okay, I see.
Thank you. Is this better? Thank you so much for saying so.
Thanks, guys.
So we want a scalable NumPy. Let's talk about that for a moment. Oh no, everything got moved around. So if I'm a scientist and I want to play with NumPy, I might go into a Jupyter notebook. I might make maybe an array of 1,000 by 1,000, just random numbers. And I like NumPy because I can do things in sort of nice, pleasant syntax. I can compute the sum. And I can do some even more complex operations like adding x to its transpose and subtracting the mean. Oops. Great. This is how you know it's a live demo. Okay. So this is nice because it's convenient. It's mathematical syntax. It's also decently fast. This is all running with nicely compiled C or Fortran code. we'd like to continue this same legacy out to bigger systems. So NumPy will fail when you try to allocate larger arrays. So here's a 100,000 by 100,000 array. It's either crash my machine or hopefully it'll raise memory error. So this is what we want to do. This is what Ryan wants to do to analyze his data sets. Fortunately, this is where Dask array comes in. So if I want to allocate an array, I can import Dask array, and it has the same API as NumPy, except that now I'm going to increase the size of my array a bit and tell Dask array to break it up into chunks. Each chunk will have size maybe 1,000 by 1,000. And I'm going to open up a dashboard here just so we can see what's going on. So when I create that array, I now have 4 cores on my laptop, and each of those cores are separately producing about 100 NumPy arrays. So each of these each line here corresponds to the activity of one of my threads, one of my cores. And we can see over time what it's doing. And it's spending, tens of milliseconds creating all of these individual 1,000 by 1,000 NumPy arrays. That Dask array is then giving us a nice logical interface over. So we can do the same things. I can ask for a little bit of data. I can ask for the sum of the data. This is going to do a lot of communication. We're communicating between processes. So we see here, we see here a lot of very fast functions for the sum, taking about a millisecond each, followed up by a fair amount of communication between those processes. And we can even do sort of the more complex operations, like what we did before. We can add X to its transpose and subtract the mean. And this is sort of the core of what Ryan wants to do with an Xarray. So here I've got it running nicely on my laptop, and we can see that Dask is handling all that administration for us. So Dask is just a very nice secretary. It allows us to break up arrays, computations in this case, but also Parquet data sets and data frame computations, machine learning things as well. It's been maybe more tuned to the scientific community than sort of your traditional industry-focused big data framework. So supporting n-dimensional arrays is particularly of value. And then, we can go to our cluster here. So if you go to pangeo.pydata.org, you can actually do everything I'm about to do. So I have the exact same environment. I'm gonna ask for maybe 40 machines. These are gonna be small, like 2-core machines. And that is also launching for me the same dashboard we had before. So those are popping up. You can see here they're increasing. We got all these machines now in the cloud. And we're going to do that exact same thing. So now instead of this array, I'm going to make a Dask array. This one's a bit bigger because I have more RAM. Let's actually make those a little bit bigger. And so now I can allocate that data and I can play with it, not with 4 cores, but with, in this case, looks like 60. I can do all the same things. And Dask is going to go ahead and handle that for me. So you can see here that so while the semantics of NumPy are the same, it looks and feels the same to Ryan, the computational performance is quite different. We've got many cores. We also have a lot more communication costs here, right? So there's a lot more red on this screen. Red is communication. And so it's now our job to try to manage that computational costs, improve things, change the algorithms as needed by scientific users. So let's go back to slides for a moment. And if you want to, go to pangeo.pydata.org to log in with GitHub credentials. It's currently entirely open access, so please don't do anything terrible. It's also completely insecure, so don't put anything secure that's sensitive up there. So let's talk about what we just did for a moment. So also, just disclaimer, Dask is not just a big NumPy. People use Dask to parallelize pandas, to parallelize subsets like scikit-learn, other machine learning tools. It's also used to build custom pipelines. If you ever applied for a credit card or traded on the stock market, you've probably touched some Dask code. So a lot of companies build Dask inside of their internal infrastructure. At a core level, Dask is a parallel task scheduler for Python. This means it's kind of like Make, if Make were designed to compete with NumPy. If that abstraction makes sense, hopefully. It's was designed to parallelize tools like NumPy and Pandas and scikit-learn. It is developed with the NumPy, Pandas, scikit-learn, and Jupyter developers. So this isn't me, this isn't Ryan, this is a bunch of people. This project came out of that community. And there are core developers of all of those projects who also have commit rights on Dask. It's lightweight, it's well supported, it's BSD licensed. But for our purposes, we care about running NumPy operations. Okay, let's skip over this. Okay, so Pangeo was designed to make this workload more friendly on distributed systems. We started with Cheyenne, a supercomputer, and more or less the HPC story has been pretty nice. So if you want to do the same thing we just did, but on your local cluster, come talk to me afterwards, point you to documentation. It's a pretty painless process. It's actually way easier than doing it in the cloud. We also then have focused a little bit on this talk on deploying cloud systems. There was a Python symposium at AMS I gave the keynote for on Monday. I gave a talk similar to this. And for that talk, we built the website that you're hopefully logging into, pangeo.pydata.org. And we built that in about a week or two. And there was a lot of challenges. Let's have a typo in there that I think I fixed. No, I didn't fix it. So there's difficulties in standing up systems. Do you use Kubernetes? Do you use Mesos? Do you use ECS? I hear it's common here. Accessibility. Can we click into things? How do we handle user management? How do we handle file formats? Do we use HDF in the cloud? How do we do that? Do we use some other file formats? There's a lot of other challenges that are not computational in nature that are sort of new for our community, right? We didn't always think about Kubernetes. That's a new, painful tool for us to learn. Oops. Okay, so we built a system. This is what you just saw. I'm going to show another example quickly, and then we'll talk about how it was built. So here is an Xarray computation. Let me restart this guy. So let's again grab a bunch of machines. So I'm going to use Xarray to look at some data that's sitting on the cloud with a new file format called Zarr. This is just the thing that we've found that has worked the best for us so far, but there's lots of choices here. And this data set is, I think, about a ½ terabyte in RAM, and it is some science stuff. Ryan could tell you more. But we've got a simulation, it's going over time, also over ensemble. And we can construct some computation. If we want to take out a variable from that, we want to take the average over time. We want to find the minimum and the maximum value over each ensemble member, and then compute that. And so that'll give us a map that's by latitude and longitude, showing us the uncertainty of temperature everywhere on the globe over time. And Dask is going ahead and it's going to go ahead and compute that on the cloud. And we're seeing that run here. So it's loading some data from the Zarr format. It's computing some means, it's loading some more data, doing a bit of communication to move around the metadata. And it's going to churn along. And it's just about done. And we can go ahead and plot that. Let's make that a little bit bigger. Right. So this is showing you a nice science result. Right, we've computed on a large data set interactively here. You can do the exact same on your laptops right now, and you can do something different. Rather than min and max of ensemble, you can try the average or the standard deviation of the ensemble. You can try different variables. You could try looking at this what it looks like over time. We see here that the simulations seem to be relatively uncertain in mountainous regions. That's not surprising. Mountains are hard to simulate around. But this is sort of the nice experience that we would like to have, that we do now have. It's sitting here on this cloud deployed system. So we're using JupyterHub for login. So if you've ever used JupyterHub before, you might recognize the login thing, with GitHub for authentication. That's running on Kubernetes, currently on Google Cloud, Google Compute Engine, but everything we've done is completely cloud vendor agnostic. So you can run it on Amazon. That seems to be the de facto standard in this community. We're also using Dask on Kubernetes for computation. We're actually living in the same cluster. We're using Xarray for user code, because again, that's what our science users are asking us for, or at least Ryan asks very loud. And for data file formats, it's sort of an open question for us. So we've tried NetCDF and Fuse. It's actually not as bad as you would think if you start doing some clever caching file system tricks. We've gotten about like 40 megabytes per second out of what should be 100 to 200 megabyte per second pipe. We've tried Zarr, which is a file format originally out of some genomics researchers in the UK, which is surprisingly well documented, well spec'd, and works nicely locally, local directories, cloud. It's sort of cloud native. It's quite pleasant to use. But again, no one has heard about it, I assume, in this room. So that provides some concerns. The HDF group is doing a great talk, I hope, later this afternoon on HSDS. They'd be fun to play with. And again, there's lots of other file formats. Most of the Python ecosystem does not build systems. We build tools that can interact with a variety of different things. So this is not GCS or Amazon specific. This is not Zarr specific. We've made a bunch of computational tools that interact pretty easily with lots of different systems. So again, we built this website over the last couple of weeks. When I say we, I don't mean Ryan and I. Neither of us are good at that. I mean these people who sort of touched that website in the last couple of weeks. They come from a variety of different institutions and are funded from a variety of different funding sources. And there's also a bunch of other people in the Dask, Xarray, and Jupyter communities that have done a ton of work. And what I want to sort of stress here is that no one person was able to build this thing. It was very easy to stand up because we tapped community expertise. The JupyterHub developers are amazing at Kubernetes, it turns out. And they're very willing to help you if you ask them nicely. I would actually extend that further to say that no single organization knows enough to stand up these services easily. And so that's why I think the Pangeo effort we've been working on has been a nice example of collaboration. The grant was very explicitly planned to have scientists like Ryan, stewards of large data and large computational infrastructure like NCAR, and open source developers like the people at Anaconda to collaborate together. And as a result, we've actually had a lot of uptake from a lot of other groups. So as an example, here's this person from UC Berkeley's Slurm Savio cluster showed up yesterday, said, hey, I've been using documentation, it's been great. I've got this problem, I can't get the flashy dashboard to work. Within about an hour, we said, hey, great, try using this NV server proxy project, came out of JupyterHub. So we're getting more and more requests like this, and it's very satisfying to see that. It's very satisfying to see many people come onto this project. Both, I think we span 2 or 3 nations now, and nonprofit groups, for-profit groups. It's been a very nice collaboration. Ways to get involved, you should try pangeo.pydata.org. Don't trust it. I will tear it down without notice, and it's completely insecure. So don't put anything there that's sensitive. You can engage, as this demonstrates. We're very friendly and very helpful. If you have a cluster you want to try things out on, let us know. If you want to try this on Amazon AWS, it is very easy to deploy on any Kubernetes system. Let us know. Contribute. We would love to have dev time. The UK Met Office has actually been really great about this. Use. It'd be nice to see people who have public data sets. Maybe we can put something together to make a couple of workflows that are easy and demonstrate how to use that data from a computational system like this, or maybe a good marriage point for a lot of the systems that you people seem to be building. We also love funding, so I have to keep paying bills. Please fund us. And that's it. Any questions? Ryan, do you want to come up too?
So I have a couple questions.
Please.
One's more targeted toward Ryan as the scientist. Sorry, you are the surrogate scientist in the room right this second.
Getting used to it.
But that's good. So I was taking notes, and I had a really interesting epiphany when you said, this is the way we want the data to look, and we want to use Python to do it, and basically stop screwing around. So my question is this.
Ryan may be biased.
Huh?
Ryan may be biased.
No, we're all biased, and that's fine. And I want to hear his particular bias because it's really interesting to me. So as you know, probably we've been working on moving NASA data into the cloud, and we're just moving it there and kind of being like, all right, guys, come and get it. So we've also spent some effort, my counterpart, Chris Linus, on thinking about ways to make the data more usable. But what I'm kind of hearing you say is just put it up there in the format that you've always been putting up in the format that you've always been putting it up there in, and we will figure it out. So you're shaking your head. So we target NetCDF, we target HDF with CF conventions. should we continue to be doing this, or should we be looking to take our data, disassemble it, put it into our own array databases that you compute on? So that's my first question. And then the second question kind of leads into, great, you're using Dask, but doesn't that require a lot of in-memory loading of data? So this is getting into more of the technical side. So are you really truly able to compute, or are you just creating an index that goes into those files, or are you creating a copy of it somewhere to act on? So those are my two questions. So one to Ryan and one more to Matthew.
Perfect. Yeah, I'll answer the first and then hand it over to Matt. So what I will say is this. The CF conventions, the netCDF data model is great. Everyone knows it and trusts it and likes it, and it seems to accommodate most of the data that we like. Now, the thing about Xarray is it's going to allow a way for that data model to persist even if we completely abandon the legacy file formats like netCDF that, you know, we're used to storing the data in. So my vision is that the logical model that was defined by netCDF and CF can live for a long time, even if there's no netCDF file under it. So that's what our Zarr implementation is. And Xarray provides a specific way for us to do that in Python. It's an in-memory, or it's a data structure. It's not a file format, right? So it provides a way for us to transition like and seamlessly from on-premises or just like laptop-based calculations to cloud. So as long as I can open an Xarray data set, I don't care at all if there's a file under it or not. Now, there's going to be different performance for different backends. And that's where there's a lot of room for development and exploration and benchmarking. Does that answer your question?
Yeah, well, it answers an aspect of my question.
Let me try to answer a different aspect of that question. So I'm often the guy who Ryan asks to try to make his thing more efficient. And so Google file formats, things like netCDF, do have problems on the cloud. It is a challenge to work with them cleanly and efficiently on cloud storage systems. What I would ask, someone who makes distributed computational tools, I think that people who make other tools would have similar requests, is please don't make a service, or if you do make a service, like give me a very nice API to it. I'd actually much prefer you just to write bytes somewhere on the cloud that are easily interpretable. I may not be dealing with your data set on Amazon, or I may be dealing with it on some other system. If I have to stand up a service in order to look at your bytes, that concerns me. But if, I think, GeoTIFF or Cloud Optimized GeoTIFF is a good example of this. They put bytes up there, there's a decent spec, I'm just using the S3 APIs to get those bytes. I'm actually happiest with that. That being said, for performance issues, there may be other things you need to deal with. Can you remind me of your second question? Second question was, how does Dask work in terms?
Are you making copies of the data with Dask, or are you indexing directly into the data?
So when Ryan is using Dask, he is creating many different functions that are going to be, like, go to this thing, grab a NumPy array out of that thing, and then do some work with that, do some work with that. Maybe after another NumPy arrays, give me a result. So we're not, Dask is a very ephemeral system. Like, we're definitely going to be bringing those bytes into memory so that we can compute on them, but we're not holding on to that data for all time. We're not a database. We're a computational system. So the workload is generally read some bytes, do some work, hopefully throw those bytes away as quickly as we possibly can to maintain memory space. This looks like any other large data computational system. Okay.
Hi. Couple questions. The nicest thing about the netCDF data model is it's actually implemented on top of HDF in most of the situations that you're talking about. And HDF has a lot of flexibility built into it, and it's used by hundreds of different disciplines, scientists in different disciplines. So the CF conventions are super groovy, and we love I work at HDF, by the way, so we love the CF conventions. But even in earth science, there are many other conventions that are used for other kinds, bathymetry data, point cloud data. And then if we look at astronomy, or if we look at, Ryan mentioned that there are a lot of other disciplines that are using Xarray and Dask. Are there other, many of those disciplines are probably using HDF. Are there other, this question really is for Matt, are you giving this talk at non-earth science, or at, say, astronomy meetings, or neuroscience meetings, or the other disciplines Are there other disciplines that are using the same framework on top of different sets of conventions for HDF is really my question.
I certainly talk to all of those communities in my role as open source Python guy for parallelism. This community has been Ryan's community has been particularly receptive to these tools, I think because they just had the need for larger computing before the other disciplines did. I don't know about their particular use of HDF. So, I mean, for example, if you talk to neuroscience guys doing cloud things, they've had to remake their own data file formats. Often they're just throwing up compressed binary blobs into S3. I think there's definitely a need for a cloud-friendly HDF-light alternative, or HDF needs to grow, indexes or something to make it easier to work on cloud.
Right, we call that cloud-optimized HDF.
Yeah, something like that, or something else. So, I mean, this is our project we picked up out of this genomics group, fit the needs that we needed. We could actually do the whole NetCDF model on it, and it was easy to move from storing it in zip files to storing it on cloud. And so, maybe that's an approach. Maybe there's other approaches. There's probably going to be a few. I think we're in a very uncertain time right now, which is unfortunate for people who are trying to push data, archival data somewhere.
You mentioned Cheyenne and the NCAR HPC. Do you know anybody that's doing this at Blue Waters?
I don't, but
Okay.
I would not be surprised.
Yeah, it'd be fun to find those people.
There's some pushback from running this type of analytics on HPC. There's some pushback in HPC environments because we're never going to be as efficient in the way we utilize that system when we're doing data analytics as you are when you're doing simulation. Right? So it's not a type of application they're used to supporting. NCAR has been very supportive, but not every HPC system administrator sees this as something they want to have running on their system.
Right.
That's not entirely true. A bunch of them many HPC administrators very much want to see their cluster utilized by all of their Python people. There actually was a grassroots campaign, please let me use my Python tools on your cluster, and they then have to achieve that.
Yeah, well, there's an interesting project at Blue Waters that integrates a lot of the observations that are made from the Terra satellite, the NASA Terra satellite, and integrates them all into a single data structure in HDF. And it would be very, for some of the projects that are trying to pull together different data from different instruments, this is a very different foundational model that I think would be really interesting to take a look at.
Yeah, and so this is actually exactly why I'm here. I'd love to talk to you further about this maybe afterwards. And to anybody else who has a different problem. So Ryan is married to Xarray, I am not. I would love to hear about your problems and see where the Python community generally can serve. That is my job. So let's chat afterwards.
Cool.
Thanks, guys.
All right, thank you.
Okay, so this concludes this session. So I do have their slides, so I'm going to try to get them up in our ESIP